Hello and welcome back. Today we are going to talk about elastic and inelastic collisions. What does elastic mean? It means that all of the energy stays in the system. If you have two objects that collide, all of the kinetic energy is going to remain as kinetic energy. What does it mean to be inelastic? It means that some or all of the kinetic energy is changed into something else, such as heat. Now, elastic collisions are a pretty special case. Conservation of momentum is true, and kinetic energy is unchanged. We can use those two facts to derive a pretty easy formula that is very often used. So let's go ahead and derive the main formula for elastic collisions. Well, first we're going to start with the conservation of momentum. So the momentum before must equal the momentum after. Mass of A times its velocity plus mass of B times its velocity has to equal the mass of A times the velocity afterwards plus mass of B times its velocity afterwards. Now let's rearrange this equation a little bit and solve for the masses. So for this equation, what we do is we rearrange our terms and then pull out the masses. So we also know that the kinetic energy in this system is going to be conserved. We can write that out in equation form with 1/2 ma VA squared plus 1/2 MB VB squared has got to equal the kinetic energy afterwards of 1/2 ma VA afterwards squared plus 1/2 MB VB afterwards squared. Now we're going to go ahead and do the same thing we did before and separate out our variables. Now to get to this point, we multiplied the entire thing by 2. We separated the variables and then we pulled out the MA and MB. So this isn't quite exactly how I want it. So let's go ahead and pull out a little algebra trick. If you remember that a squared minus b squared has got to equal a minus b times a plus b. We're going to use the same fact in the next step, and that is to break the squares. So now let's look at what we have. We have conservation of kinetic energy in this formula. We've got conservation of momentum in this formula. There's a lot of similar terms. If you look close, you can see we can actually divide our terms. And when we divide it, we end up with this equation. The velocity of A plus the velocity of A after equals the velocity of B plus the velocity of B after. Why don't we rearrange this equation a little bit to see the before and after terms? So the velocity of A before plus the velocity of B before has to equal the negative of the velocity of A after minus the velocity of B after. Pretty cool that it all cancels out and breaks down to something simple like that. Okay, so now it is imperative to note that when you start plugging in numbers, you get the signs correct. The signs do mean something. They mean the direction of travel. Only when you put in the appropriate signs will you get an appropriate answer out. So let's go ahead and do a couple of problems. In the first problem, we have a billiard ball, A, of mass m that's moving with speed v, and it collides head-on with another ball, B. It's of equal mass and it's at rest. What are the speeds of the two balls after the collision, assuming that it is a perfectly elastic collision? Okay, so what do we know? We know that the velocity of A equals v. We know the velocity of B equals 0. We also know that mass A equals mass B equals, we'll just call it m. Perfectly elastic collision, so we know that conservation of momentum must hold true. So we know our terms before mass A, velocity A, plus mass B, velocity B, equal our terms after mass A, velocity A prime, plus mass B, velocity B prime. We can go ahead and plug in what we know into this formula. We'll end up with mv equals mv prime A plus mv prime B. We'll notice that the m's cancel out, and we're left with v equals v prime A plus v prime B. So we're stuck here. We have one equation and two unknowns. We need a second equation. So we can go ahead and use the equation that we just derived. Let's go ahead and give me a little more room here. So velocity A minus velocity B has got to equal velocity prime B minus velocity prime A. Our VB obviously cancels. Our VA equals V, so V also equals VB prime minus VA prime. Now we can equate the two of these together to get V prime A plus V prime B equals V prime B minus V prime A. There's a VB on either side. We go ahead and cancel them out. Put the VAs on one side. We're going to notice that VA, actually two of them, VA prime, equals 0. So it actually doesn't matter how many VA primes there. VA prime equals 0. So now let's give me a little more room. So with this newfound variable, we can go back to our previous equation. Our V equals V prime A plus V prime B. We can see that our VA cancels out. Our V prime B has to equal V. So what we have here are three moments in time. The first moment, we've got our ball moving along with a certain velocity. We have a second ball just sitting there. At the next moment in time, our two balls meet, this instantaneous moment in time. The instantaneous moment after that, our first ball is going to be not moving. Our second ball will be moving with the same velocity that the first ball started with. Interesting. So let's look at the next problem. Ballistic pendulums, one of my favorite toys. The ballistic pendulum, it's a device that is used to measure the speed of a projectile, such as a bullet. The projectile, we'll call it mass little m, is fired into a large block of mass, we'll call it big M, which is suspended like a pendulum. As a result of the collision, the two masses, little m plus big M, swing up together to some height h. Determine the relationship between the initial horizontal speed of the projectile, v, and the maximum height, h. Now this is a really cool concept because we're linking our two concepts together. We're linking conservation of momentum and we're linking conservation of energy. So if we look at this first situation, we know that momentum, at the instant the bullet hits our ballistic pendulum, the momentum is going to be conserved. The P before is going to equal the P after. So we have a little m v has got to equal little m plus big M times v naught, where v is the velocity of the bullet before, which we're actually interested in, so we should solve for that. V equals m plus big M all over m times v prime being the velocity of the ballistic pendulum plus the bullet inside of it. Now if we look at the second situation, the situation where this actually turns into a pendulum, what we know is the energy should be conserved, ignoring, of course, any small amounts of friction that are happening in the rope. So our kinetic energy plus potential energy before has to equal the kinetic energy plus potential energy afterwards. So our kinetic energy in the beginning would be 1/2 little m plus big M v prime squared plus, if this is our 0 point down here, potential energy would be 0. It's got to equal the kinetic energy after. Kinetic energy up at this point here, our velocity is 0, so kinetic energy is going to equal 0, plus our potential energy at the top, which would be our mass times gravity times the height we're at. Now we can go ahead and solve this real quick. Cancel out our m's. Our v prime is got to equal the square root of 2gh. Alright, let's give myself a little more room here. So we can plug what we just found into the equation we had just a moment ago. The velocity of the bullet, the velocity of the projectile, is going to equal the mass of the projectile plus the mass of the ballistic pendulum divided by the mass of the projectile times the square root of 2 times gravity times whatever height the pendulum rose to. Pretty cool. Wait till Wednesday and we'll see a really good demo of this. Thank you for watching, and don't forget to check as you learn and complete the rest of tonight's homework assignment.